Hi, so I'm Chandler, and this is my FEA final project. It is a design development project focused on heat transfer analysis in a room with an open window. So the purpose of the model is to inform the design of a temperature-sensitive casement window. This system operates using a DC motor coupled to a gear system to open and close a window to control temperature in a room. So we were having a problem with how and where to measure the temperature input, and so we will use the time and space dependent temperatures and heat flows to evaluate this. And our design parameter that we will look to vary is the location of the temperature sensor. So improvements to the system that can be made are easier adaptation based on where we locate the temperature sensor, simpler circuitry, and versatility of where the temperature is to be measured. So the models we used were a 1D analytical model using MATLAB with background heat transfer theory such as internal, external, and natural convection and conductive heat transfer to compute temperature and heat flow distributions. Then we used a 3D and 2D FEA. The 2D FEA uses the length width plane of the room to model areas with the largest temperature variance, and the 3D FEA uses the entire room to measure the temperature variance throughout the whole room. Assumptions to be made are no thermal energy storage, uniform wind speed and ambient temperatures, and of course the 1D, 2D, and 3D models all vary in assuming where the temperature varies. So the 1D only varies along the length, 2D only along the width and the length, and the 3D along all three axes. So the 3D model development was done by making a SolidWorks multi-body part with an inner body to represent air and the outer body to represent the wall. And in ANSYS, custom materials were made for air at 300 Kelvin and the wall to combine all thermal properties of the components, such as siding, wood, drywall, and insulation. And then these models were opened in ANSYS mechanical. Boundary conditions were added for convective heat transfer on the front and back walls due to a uniform wind flow, convection from natural convection inside the room, and perfectly insulated boundary conditions on the side and the roof and the ceiling. And then this was solved for spatial and time dependent temperature and heat flow distributions. So here are our results. We got a logarithmic pattern for increase in temperature and decrease in heat flux as time goes on. So here's our results for temperature. You can see that all regions of the room heat and the middle of the room remains coldest. And same thing with heat flow, that there's most heat flux around the outside the room and it is minimal in the inside the room. So our verification is that these results are generally close to 1D and 2D models, although this does not reach steady state due to increasing effective thermal resistance with time accounted for in ANSYS. And our validation is that, of course, these match expected results where temperature increases near the beginning of the time interval, since there's a larger temperature difference. And so we will go to our parametric study next, where we varied temperature difference and convection coefficient by changing wind speed. So with temperature difference, we follow similar trends where temperature varies most near the beginning, of course, and the middle of the room remains coldest, whereas wind speed actually changes the steady state value of the room for the same temperature difference. So changing wind speed changes convection coefficients most so on the front wall, and it reaches a temperature value closest to steady state value, whereas the other one does not reach as close. So this model is most useful for high convection coefficients and short periods of time, beyond what can be compared in MATLAB using background heat transfer theory. So our conclusion is that this 3D FEA model provided an accurate overview of the situation, and as expected, temperatures and heat flows vary most near the heat sources and follow logarithmic trends. These trends can be used to move the temperature probe in the casement window to the wall of a room rather than using a central location where it is to be measured while still retaining accuracy by looking at this graph. which shows basically there will be a delay between the increase in the center of the room and the increase at the front wall or the back wall, which can be accounted for. So thanks for watching, and questions and feedback are welcome.